Hey everybody, hope you're doing well. Today's video is about angles, which is section 5.2 in the book. In our last video, we talked about circles. So an angle, again, is something you're all probably familiar with, but we'll get a little bit technical about it and introduce some terminology. An angle is sort of the space between two lines that emerge from a single point. So we'll call them rays because they only extend in one direction. We'll designate one side as the initial ray and the other side as the terminal ray, and we will give angles a sort of direction. So we'll imagine this angle kind of opening from the blue ray to the terminal ray, and the angle is kind of the space in between. Because of this direction, we will use a positive angle if the opening is in a counterclockwise direction. So this on the left here, we open from blue to purple. That's a positive angle. And if we open the other way, so if we designate the purple ray as the initial and the blue as the terminal and open this way as on the left, that's a clockwise rotation, and that will be a negative angle. So these two angles have the same magnitude, but they're different signs, right? This is a positive angle, and that is a negative angle, positive on the left, negative on the right. We will generally put our angles in standard position, right? So I could take any one of these angles and sort of rotate it around and move it around the page. As long as I don't move the blue and the purple rays closer together, I don't change the size of the angle, but this can get confusing. So we'll put our rays often in standard position and all that means is we lay the initial ray along the positive x-axis. So we put the point where the two rays meet at the origin, lay the initial ray horizontal on the positive x-axis, and now positive angles kind of open upward counterclockwise and negative angles open downward clockwise when we're in this position. So you're probably familiar with degree measure from angles. You've all heard of and probably worked with 90-degree angles and 45-degree angles and so forth. The way we define a degree, this unit, is it's 1/360th of a complete rotation. So this is kind of an old-fashioned way of measuring angles, but still very much in use, right? So one complete rotation, if we start again on the positive x-axis and rotate all the way around and come back where we started, that is an angle. That's a 360-degree angle. So 360 is, that's a pretty fine division of the circle. So there is a 1-degree angle, and you can see it's pretty small because there's 360 of them in the entire circle. So if we sort of step that up, you can see I'm just adding a degree every time I click on that plus sign. And since there are 360 degrees in the circle, 1/4 of 360 is 90. So 90 degrees is what you expect, right? 90 degrees, right angle. And 180 degrees is half of that, right? So that goes halfway around the circle. And so forth. And 45 degrees, 45 is 1/8 of 360. So that's 1/8 of the circle, sort of a perfect pizza slice. Okay. Let's open this one up. There we go. So angles are certainly connected to circles. We usually visualize and think about angles inside a circle. Like this one. The circle that you're looking at in this picture is called the unit circle. Its center is at the origin and it has a radius of 1, right? You can see that this is the point 0, 1 up at the top, and this is the point 1, 0 over on the right. So we talked about circles last time, but we didn't talk a lot about measuring circles. We just talked about their equations and finding places where they intersect with lines and stuff like that. So one of the most famous facts about a circle is that if you take the ratio of the length of the circle, so that's the distance around the circle, right? If you laid a string around the circle and then straightened it out and measured it, that's called the circumference of the circle. And the diameter of a circle is the distance across, right? So we take a line that runs through the center and the distance between the points where it hits the sides of the circle is the diameter. Again, I think you're probably familiar with those terms. And if you take the circumference and divide by the diameter, it's always the same value. That's what the number pi is. And again, I'm sure you've seen the number pi before. It's one of the most famous numbers in mathematics. This fact that circles have this constant ratio of circumference to diameter has been known for thousands of years. And the value of pi, which is necessary in computing almost anything about a circle, has been, because folks have needed to use that value in constructing things, it's been approximated in lots of different ways by lots of different cultures. There's all kinds of information on the internet about various approximations to pi. Pi is an irrational number, which means in essence we have to approximate it because this decimal expansion, which is very famous, goes on forever. It doesn't repeat, it doesn't terminate. So since it goes on infinitely, we can never write it all down. We'll have to approximate whenever we do a numerical calculation. Okay, so here is a quick illustration of this, I think. So here I have a circle. The circumference is in blue, right? Its distance around. The diameter is in purple. The distance is straight across. And I'm having the computer divide one by the other. And as I change the radius, so I make the circle smaller, you can see those top two numbers get smaller, but the ratio never changes, right? Whether I make the circle big or small, circumference divided by diameter is always equal to pi. Okay, so this means if we accept this fact, that C over D is equal to pi, and the diameter, of course, is twice the radius. The radius is halfway across the circle. The diameter is all the way across the circle. And if you put a 2r in for D down here in the bottom, there we go, you can solve for the circumference and you get this formula: circumference is equal to 2 pi times the radius, which again, I expect you've probably seen before in geometry. So an angle, another way to measure angles, and the way that we are going to use more often and the way that it's much more common in mathematics, is using something called radian measure instead of degree measure, right? So we talked about degree measure before. How do you measure an angle in radians? Well, you put the angle in standard position inside the unit circle, right? So in a circle of radius 1, and the amount of the circumference that it subtends is called the radian measure of the angle. So let's go to a quick picture here. Right, so this is an angle that measures 1 radian. And what that means is that the measure of this black arc along the outside is 1 unit, right? So if you laid a piece of string over the top of that and then straightened out the string and measured, that's one unit of distance. And so this is 1 radian. So in the entire unit circle, right, remember we're in a unit circle here, circle radius 1, the circumference of the circle is 2 pi times the radius. So that's 2 pi times 1, which is just 2 pi. Pi is about 3.14. So 2 pi is 6 1/4 about. And so this is, roughly 1/6 of the unit circle. Not exactly, because the total distance is 6.28, but roughly 1/6. And so there's 2 radians, 3 radians, right, is almost halfway. I know if I go halfway, that's going to be 1 pi. So I'm almost there with 3, right? Because pi is a little more than 3, 4, 5 radians, 6 radians, not quite the whole way, right? Because the entire distance is 6.28. It's a little more than 6. Okay, so that's how we do radian measure. Let's talk a little bit about going back and forth between these two ways of measuring angles. The key to this, again, is the entire unit circle is 2 pi in length. So 1 complete rotation is just 2 pi radians. But we know 1 complete rotation is 360 degrees. And so this gives us a bridge from degrees to radians. 2 pi radians is equal to 360 degrees. And consequently, if I take this equation and I divide both sides by 2 pi, so this equation right here, I divide both sides by 2 pi, then I just get 1 radian on the left, and I get 360 divided by 2 pi, and I can reduce the fraction a little bit to 180 over pi degrees. This allows me to convert from radians to degrees. And I can rearrange the equation, right? So if I take this equation and I divide both sides by 360 instead of dividing by 2 pi, then I get 1 degree on the right-hand side, and down here I switch sides. And on the other side, I get 2 pi over 360. You can reduce the fraction a little bit, 2 pi over 180. So I know how many degrees in 1 radian, I know how many radians in 1 degree, and that means even if I had an angle like, 48 degrees, right, some degree measure angle, well, 1 degree is this many radians, so 48 degrees is 48 times that many radians, right? So just 48 times pi over 180. You can do a little reducing of the fraction here, and if you do this on your calculator, it comes out to be about 0.84 radians. And we can go in the other direction just as easily, right? If I have some radian measure, say 1.23, notice a radian is considerably bigger than a degree, right? So, we saw up here, a radian is a good chunk of the circle, whereas 1 degree is a tiny angle. But if I have some angle in radian measure, I know that 1 radian is this many degrees. So 1.23 radians is 1.23 times that many degrees. And if you do this blue highlighted calculation on your calculator, it comes out to be about 70.5 degrees. Okay, so we have 2 different ways of measuring angles. We tend to prefer radians, but degree measures do come up. So it's useful to be able to go back and forth between the 2 measures. Some major correspondences between the 2, right? Starting at the bottom here, 180 degrees is half of the circle, and that's pi radians, right? Because the entire circle is 2 pi radians and 360 degrees. So a quarter of the circle is 90 degrees. 1/4 of 2 pi, right? If you take and do this calculation, let's do 1/4 of 2 pi. 1/4 of 2 pi, you can cancel a little bit, right? The 2 with the 4, and you wind up with pi over 2. And that's where this value comes from. And we just do a similar thing for these other ones, right? 60 is 1/6 of 360 degrees. And if I take 1/6 and multiply by 2 pi, I get pi over 3. 45 degrees is pi over 4. 30 degrees is pi over 6. Again, the first column here is the radian measure of the angle. So all of these folks are radian measures. These are the degree measures of the angles, and then the fraction of the entire circle that the angle takes up is in the last column. Okay, so again, this has all been about converting from degrees to angles. We talked earlier about what we mean by a negative angle. So we can make sense of positive and negative angles. They just open differently from the positive x-axis. We can also make sense of angles that are bigger than 360 or 2 pi by just rotating around the circle as many times as we need to. So 2 angles that are in standard position are called coterminal if their terminal sides all coincide. So here's an example in this picture, right? So if I open an angle from the blue ray to the purple ray, just like this inside angle, inside arrow right here, right? So that's some angle. But I could also start from the blue ray, open, and just keep going all the way around, all the way around, all the way around, and keep on going right past the beginning and then stop here, right? So in this picture, I believe that this angle is a 45-degree angle. It looks like that, right? So the first angle is about 45 degrees. Let's put a little degree sign up there. There's degree sign, okay. And the second angle, and so when I say first, I mean the one with the arrow on the inside. The one on the outside I go 360, and then I go another 45, right? So this is going to be 360 plus 45, and that comes out to what, 405 degrees. There. So these two angles, 45 degrees and 405 degrees, are coterminal. And there are lots of different angles that are coterminal, right? I could just keep adding another. If I add another 360, that just means I go around the circle twice before finally landing on the purple line. All right, so that's coterminal angles. A little more about measurements. And here, I think the picture is going to be useful to have while we talk about this. Let's open up the picture. Okay, so here I have an angle theta, right? So that symbol right there where the cursor is the Greek letter theta. And so the angle in the unit circle subtends this blue arc, right? So an angle subtends a piece of the circle. That's a technical term, right, for the arc of the circle that the angle sort of makes. So you can see this inner radius, the radius of the small circle here is 1, and then I've drawn another bigger circle around the unit circle that has some unknown radius r. So the angle subtends one arc on the unit circle, and it subtends a bigger arc s on the outer circle. And s makes up the same fraction of the circumference of the big circle that theta does of the little circle, right? So the big circle has circumference 2 pi r, the little circle has circumference 2 pi times 1, or just 2 pi. So the fraction of the big circle that s takes up is the same as the fraction of the little circle that theta takes up. So that's where this equation comes from right here. I can multiply both sides by 2 pi basically, and the 2's and the pi's all go away. And this just boils down to a much simpler equation, s over r equals theta. And if I solve for s, what I get here is a formula for the length of the arc subtended by the angle theta on any circle, right? Because you could put theta inside a unit circle or a circle of radius 5 or a circle of radius 10 or what have you. And now we have a pretty easy way of calculating the length of this arc on the outside. All right. The area of a circle, so we've been talking about circumferences and lengths. So that's a one-dimensional measure. Area is a two-dimensional measure. And I'm sure you've all seen the formula pi r squared. This is unfortunately a difficult formula to prove, right? So we just actually have to accept that this is the area of a circle. But why is that true is a good question. It's just beyond the scope of this class. Okay. So the area of a circular wedge, right? So now we know what the area of the whole circle is. How would we find the area, say, just of this pizza slice over here that's kind of made by the angle theta? Well, again, it takes up the proportion of the whole area that that the inner wedge takes up of the unit circle area, right? So if I take theta over 2 pi, right? That's the fraction of the whole circle that the angle makes up. I just have to multiply that by the area of the big circle. And again, the pi's cancel. So I just wind up with theta r squared over 2. So the upshot of these calculations is if I have some sector of a circle like this, again, think of a pizza slice, I have nice formulas that if I know the angle and I know the radius of the circle, I can figure out the length of the arc and I can figure out the area of the slice. Okay, so let's, I think, just go into some examples here. That's that's all the sort of theory that we need to cover. All right, so how do we get the circumference of a circle like this? So notice here, I haven't drawn a picture of the circle or given you its key dimensions. Rather, recognize this as the equation of a circle from the previous video. Okay, well, because it's in this form of the equation of a circle, I can spot the center, right? 3 is the x-coordinate of the center, -1 is going to be the y-coordinate, and I know the radius, right? That's r squared on the right-hand side, so the radius must be 9, and if I know the radius, of course, I can find the circumference, right? If the radius is 9, then the circumference is 2 pi times 9, or 18 times pi, which on my calculator comes out to be about 56.5. Okay, so suppose I have an angle in standard position and it subtends 2/3 of the unit circle. what is its degree measure, and what is its radian measure. So the key thing here to remember again is that one complete revolution of the circle is 2 pi radians, right? So 2/3 of that is 2/3 times 2 pi radians. Hopefully that's the first thing we do here. Well, actually, so I did degrees first, which is fine. So there's 2 pi radians or 360 degrees in the entire circle. So 2/3 of 360, that comes out to 240. So the angle of degree measure is 240. And of course, we can go back and forth between radians and degrees whenever we want. Or I could just do what I suggested first and take 2/3 of the entire circle in radians. 2/3 times 2 pi comes out to 4 pi over 3, that. And on my calculator, that's 4.19. All right, so I have the degree measure here and the radian measure here of the angle. And these exercises, of course, are coming from the notes and exercises. So that's where you can find those numbers. So exercise 515, I'm going to pause for 1 second. Okay, so we were, I paused there for a second. We're going to look at exercise 515, and I just wanted to get that exercise up. So here it is, right? So we start with an angle in degree measure. Theta is 35 degrees. First thing, indicate it in standard position. That just means draw a picture of the angle in standard position in a circle of radius 3. So I'm going to draw a circle of radius 3 centered at the origin. The initial ray of the angle will be on the positive x-axis. 35 degrees, so that's a little less than 45 degrees, and you wind up with a picture that looks like this, right? So you can see my circle of radius 3, and there's my angle. Okay, what else do we want to figure out here? Radian measure, length of the arc, and area of the sector are the three things we need to do. Okay, radian measure, so that's a simple matter of conversion. The conversion factors, if you don't remember them, they're in notes, of course. But I know that 1 degree is that many radians, so 35 degrees is 35 times that many radians. So I just multiply 35 by pi over 180. You can reduce the fraction to get the nice exact value, or do it on your calculator to get an estimate. So about 0.61 radians. The length of the sector, remember the formula is S is equal to R times theta. That formula, by the way, it's worth emphasizing here, has theta measured in radians. So when you use this formula, make sure theta is in radian measure. Same goes for this formula, right? So the our arc length and area and wedge area formulas both require the angle to be in radian measure. So that's okay. Now I have the radian measure of the angle right here. So I can just use S equals theta times R, right? So theta times R, whoops, forgot an equal sign there. Theta is, R rather is 3, theta is 0.61. And so I come out with 1.83 is the length of the arc. So that's the length from here to here. And then for area, I use the other formula, right, which is theta r squared over 2. Right, so there's the formula. Again, I'm careful to use radian measure, right? So there's the value of theta, and r is 3, right? So I get a 3 squared. I do that on a calculator, and I come out with that number for the area. Okay, let's try to find an angle that is coterminal with 420 degrees, and we're looking for one between 0 and 360. Again, when we have like a large angle like this, it just means that that angle effectively wraps around the circle multiple times. So we're just going to keep subtracting 360 from this figure, because when I subtract 360, I just go one less revolution around the circle, right? So this angle, 1420, and this angle, 1060 in degrees, those are coterminal, right? Angles that differ by a multiple of 360, visually, they just differ by some number of complete rotations around the circle. And so their terminal sides are the same, they are coterminal. So I'll subtract 360 again. And I get 700. I'm still not in the desired range. Now I have 3 angles that are coterminal here, 700 degrees, 1060 degrees, and 1420 degrees. And I think one more subtraction. This is certainly not the most sophisticated way to do the problem, but it works, right? So when we subtract 360 again, now I have 4 coterminal angles, and this last one is the one I want because I'm looking for one that doesn't involve a sort of an excess rotation around the circle. So 340 degrees is the answer that we're looking for here. There. All right. Okay, last example, and that will be good, I think, for angles. The radius of the Earth. I think that this actually varies a little bit with seasons, and the Earth is also not quite a perfect sphere, but it's a decent approximation. And the last time I Googled it, it came out to be about 3,960 miles. So what I want to do is find the distance along an arc on the surface of the Earth that subtends a central angle of 1 degree, right? So in other words, if you take the center of the Earth as sort of the center of the circle and make a 1 degree angle, so that's a pretty small central angle, how much arc length, how much distance along the surface does that subtend? Well, I know how to find arc length using S equals theta r. Where do we do that? Right here, S equals theta r. But I need theta to be in degree and to be in radian measure, pardon me, when I do that. So I don't want to use the 1 degree. I want to convert to radians. Of course, 1 degree is, I guess, so that's what we just said, right? Use that formula when theta is measured in radians. 1 degree, of course, is pi over 180 radians. So I can use this in this formula. I know the R value is given the 3960. So when I plug in, I get pi over 180 times 3960. And on my calculator, that comes out to be about 69 miles of length along the surface. All right, so that is good for angles. Take good care of yourselves, folks.